All right, in this section, we're going to begin a study of something new called set theory. It's a little bit different than something you probably have ever seen before. This first section has a lot of notation, but not a lot of computation. So let me write up some definitions to start us off. A set is a collection of items where it is easy to tell what the items are. As an example, let's take a look at the set of numbers, the set of whole numbers between 6 and 13. The way it's going to look then is we'll actually include 6 and 13, even though I said between. When I say between, we mean the ends as well. So between 6 and 13, I'm going to get all the whole numbers between them, strictly between them, and including them. If I wanted to not include 6 and 13, I would have said strictly between, and that would have taken out the 6 and the 13. Notice that it's easy to tell which items are in this thing because, well, they're just plain listed out. They're not always going to be listed this way, but when they're listed like that, it's extremely easy to tell what's in them. Another set that you're probably familiar with is called the natural numbers. And the way they look, they usually use a letter N with a weird kind of a double strike on the long leg. And that's going to equal these. I'll have 1, 2, 3, 4, and it'll just keep going on forever. So here, while I'm not able to list every item in the set, I am able to tell you which items are in it. For example, I know that that letter N is going to contain numbers like 5,000,000, 100,000, 74. I know also by looking at it that it's not going to contain any negative numbers. I know that it's not going to contain 0, for example. That's plain because of the way it's listed out. Another one we have is called the integers. They have a strange symbol. They have a Z, a weird looking Z like this. And it's like the natural numbers, except it's got more items. It's got like the natural numbers are inside of it. So here, I've made a couple of uses of this stuff here, these ellipses. Ellipses means the pattern continues. So if I just say the pattern continues, that keeps going on, and so there's no way of telling how many items are in the set N because, well, it's called an infinite set, so I can't actually list or count the number of items in it. The same with the integers Z. They're an infinite set, but notice that I've got ellipses on the front and the back of them. That means that those things are going to infinity in the positive numbers and are also doing it through the negative numbers. Now all of these, it's very easy to tell what the items in the set are. Sometimes they have to invent a new notation if they can't list them like these. One such example are these, the rational numbers. Here, it's going to look strange. We use the letter Q for quotients. And the way this it looks like A divided by B. That bar means the word such that. A and B are integers, and B furthermore does not equal 0. So what this does is it tries to list the shape of each of the items in the set. So Q, for example, I could see things like 1/2 are in there. Since A and B are integers, it means they can be negative as well. So like -3/8, 5 21sts. You can even go with the other. You can have like 9/4. All of these you can see are rational numbers. They have a numerator and a denominator. However, there's other numbers in there that you may not explicitly think that are in there until you look at this. What about the number 5? Is the number 5 a rational number? And it is. Because you can take 5 and change it to 5 divided by 1 and it still is equal to 5. So every integer is inside of there. Because I can take every integer and write it as a fraction like that. So the rational numbers contain the integers inside of them. In fact, 0 is even inside of the rational numbers because 0 is still 0/1, for example. A specialized set is called the empty set. We use this symbol, the Greek letter phi, and it is a set with nothing inside of it. So this here is sort of like the mathematical equivalent of 0 if you were adding and subtracting. So this is a mathematical system that has activities that are similar to addition and subtraction and things like that. And so this item here plays the role of like a 0, but not quite in the way you think it does. Now once we come up with empty set, I need also to list this item here. That symbol, that weird looking symbol there, it's not a Greek letter, although it looks like it would be epsilon, but it's not quite. This thing here means the phrase is a member of. That's exactly what that symbol means. So let me write up an example here. Suppose I use the letter D and I write X such that, remember that line means such that, X is a day of the week. I could have listed all of them out. In fact, if I wanted to list them all out, I would do Sunday, Monday, Tuesday, Wednesday, Thursday, Friday, and Saturday. So one of the things, I've not mentioned the basic structure of these things at all. I've just sort of started writing out sets. But notice I use curly brackets or curly braces around the outsides of the set when I actually write it. In the first example here, where this D right here, this is called set builder notation. Sometimes it's easier to use that than any other method that you can think of. But I could also have written out those things I could have written D out explicitly like I did in the second formulation of it here. Well, it's easy to tell what's inside of there, so I can use this. I can say, for example, Tuesday is in set D, or Thursday. That's also in set D. However, I happen to know that numbers, for example, 29 is not in set D. Notice I just put a slash through it. Or the month of May, I know, is not in D. For this example, I'm going to give you a set listed explicitly, and I want you to use set builder notation. So rewrite the set 35, 40, 45, ... You know what that means? All the numbers in between are inside of there, up to 95. So I'd like to rewrite that in set builder notation. So we could use, let me see, did I give a name to this thing? I did not. Let me call this by a name. Let me call this A equals. We usually use capital letters to list the names of sets. So in set builder notation, the same set A could look like this: X such that X is a multiple of 5 and X is between 35 and 95. Next topic is cardinality. This is the size of a set. So for example, if A equals 1, 2, 3, 4, 5, the number of items in A is designated by N with A in parentheses. That equals 5. So N of A lists of the cardinality. B, suppose this set is 5, 10, 15, ... 100. The number of items inside of B equals 20. Now for our natural numbers, 1, 2, 3, 4, and they went on and on and on. The number of numbers inside of that set is infinity. So what we have here are these two items are finite sets because you have, well, a finite number of items inside of them. And then, of course, N sets like that are referred to as infinite sets. Consider the following set. V equals X such that X is a vowel in the English alphabet. Then the size of V, the number of items in V, is equal to 5 because it's generally accepted that there are 5 vowels. That's why I called the set by the letter V. There are 5 vowels in the English alphabet. So they are A, E, I, O, and U. I'm not counting Y, even though some people try to do that sometimes. In a set, the order does not matter. So for example, in the set V, which I wrote as A, E, I, O, U, that's the same if I jumble up the items E, U, I, A, O. These are the same things. So the order is not that important. It's not important at all. All we're really trying to do is to list out the items in there in whatever order we want. So here I have two finite sets. Notice this. No matter what item is in B, that item is also in A. So just take a look at the things that are in B. B contains the numbers 3, 7, and 11. If you take any of those things, 3, take 7, take 11, notice every single one of those is also in the set A. So since that is true for every single item in B, we say that B is a subset of A. This notation is something that we'll talk about in the next video, but for now, I just want you to see that. Notice though, on the other way, that not every item in A is also in B. So the other way doesn't work. There are items in A that you will not find in B. For example, the number 1 is inside of A, but the number 1 is not in B. So 1 is in A, but 1 is not in B, for example. So that means that A cannot be a subset of B. And that's something that's nice about mathematical notation, is that when I want to say not, I just simply put a slice through the thing, and that means not.